All right, welcome everyone. Today we're going to look at how to calculate trigonometric integrals where we have powers of tangent and secant. So integrals of the form tan of x raised to the power m times secant of x raised to the power n. We're going to start this today. And the strategy is going to feel fairly similar to what we saw with our trigonometric integrals involving sines and cosines. So we're going to have developed similar strategies. So what's the strategy we're going to look at today? Well, it kind of centers around using substitution rule. So we're going to let either u equal secant x, or we're going to let u equal tangent x. So remember, we're going to be looking at how to do an integral involving secant terms times tan terms. So those are going to be our two possible substitutions. Either let u equal secant or let u equal tangent. And which one we use ultimately comes down to our differentials. So we know that the derivative of secant is secant times tan. So if we're going to let u equal secant x, the differential then, it has to be secant x times tangent x dx. Same thing for tangent. If we're going to let u equal tangent x, well then what's the derivative of tangent? It's secant squared x. So our differential then has to be secant squared x dx. And so we're going to start by looking at our integral, and we have to make the differentials match. So we're going to look at the function we're integrating, and our first step is to try to factor off either a secant x times tangent x to make it match up with this differential, or we're going to factor off a secant squared x to make it match with this differential. And whichever one we factor off, we're going to put that next to the dx. So we'll have a nice perfect match then for our substitution rule. All right, so let's look at the kind of the strategy more specifically. So let's say we factor off secant x times tangent x and we put that next to our differential. Well, in that case, how are we going to proceed with our integration? Well, we're going to convert everything, all of the remaining trig terms in our integral then to secant x. And it might be helpful just to kind of remember what our possible substitutions and what our differentials would be. So if we're letting u equal secant x, the differential du then has to be secant x times tangent x dx. So if we factor off this secant x times tangent x, if we're in this first strategy here, well then we're going to let u equal to tangent or secant. So what we want to do then is in our integral, we want to have only secant terms. And then we'll be able to go through our substitution. So we would let u equal to secant x, and then we would go through our regular substitution rule. If we go the other route, and we say factor off a secant squared, well then let's write down what our substitution would be in that case. So let's say we go through our integral and we factor off a secant squared. Well, in that case, secant squared is what's going to become our differential. So we want to have only tangent terms because that's what we're going to choose for u in our substitution. So if we factor off a secant squared, we're going to go through our integral and get rid of we'll convert all of our trig terms to tangents, because then we'll be able to go through with a u sub and finish integrating that way. And so the key phrase here is, how are we going to be converting secant terms and trig terms back and forth? Well, we have a nice trig identity related to that sine squared plus cosine squared equal to 1, but we have one now for secant squared and tangent squared. So what does it say? Well, it says secant squared of some angle is equal to 1 plus tangent squared of some angle. And this allows us to kind of convert back and forth between, secants and tangents. All right, so we're going to see how this works. So the main thing is when we're presented with our integral, we want to try to factor off either a secant times tan, or we want to factor off a secant squared. This first option here, factoring off secant times tan, this one works generally if we have an odd power of tangent. And if we're going to factor off a secant squared, well, that one has an even power of secant, so we need to have an even power of secant in our integral. So you can use that to help identify which one of these methods to use. If our integral has an odd power of tangent, well, this differential has an odd power of tangent, so that's what you're going to factor off, and then you'll go through these steps. If our integral has an even power of secant, well, this differential has an even power of secant, so this is the choice you would take. So let's try it out. It'll help to see a couple examples. So let's start with example 1. Here we have the integral of tangent x raised to the power 6 times secant x raised to the power 4. We're going to do the integration. And when we look at this, we have an even power of secant x. So when we look at our powers of tan and secant, tan is an even power, so that doesn't really tell us anything at this point, but we have an even power of secant. So what we can do is we can factor off a secant squared. That's the good thing about having an even power of secant, is we can factor off a secant squared. So let's actually do that. So what we're going to do is we're going to keep everything the same, at least at first, and we have secant raised to the power 4, so let's split that up, and we'll write it as secant squared x times secant squared x. So we're just splitting that up. We're factoring off a secant squared, and we're putting it next to the dx. So let's that secant squared now, that's kind of reserved. We're gonna use that for our substitution rule. That's going to become part of our differential. So we'll tuck that away next to our dx there, kind of put that out of mind for just a second. That's going to become our differential once we do the substitution. Then, so we've factored off secant squared. What we want to do next then is we want to look at everything that's left over, and we want to convert all of the secants that we see. We want to convert everything to tangent. That's in here. We want to convert everything that's inside there. All the remaining terms, we want to convert those to tangent x. And the reason is because this is going to be our differential. Later on in our work, we're going to let u equal tangent x, and du is going to become secant squared x dx. So, if this is going to be our differential, that means we have to pick u to be tangent, and that means in our integral, everything here has to be a tangent term. So the tangent raised to the power 6, we're good with there. We have to convert this secant squared. And the way we do that is we do it with that trig identity. So we know secant squared x is equal to 1 plus tangent squared x. That's our trig identity. The way I kind of remember that trig identity is I have a plus next to the tangent, and the plus, I generally kind of write plus signs and t's kind of similar. So that's how I remember it. You know, you just need to memorize that trig identity. That's what works for me. So I know secant and tan are on opposite sides of the equality, and the plus and the t kind of look similar. So there we go. All right, so let's actually fill that in. So we know what secant squared x is equal to. So this is going to become 1 plus tangent squared. So we're going to have the integral of tangent raised to the power 6 times 1 plus tangent squared x. And then we still have that secant squared x dx there at the end. And now if we look at this, everything, we're in good shape. We're in good shape for our substitution. So we know secant squared x dx, that's going to become du, kind of by design. And then everything else that we have, all these other tangents that we have, we know u is going to be equal to tangent. So this is going to become a u to the power 6. This is going to become a u squared. And so we just kind of go through our substitution rule now. So we end up with u to the power 6 times 1 plus u squared. And then the secant squared dx, that's going to become our differential du. All right, so let's kind of just go back through what we did here. Saw we had an even power of secant, so we factored off secant squared, put it next to the dx. That meant we hopefully, if everything works out, that would become a part of our differential. So the secant squared x dx would become part of our differential. So that tells us we're ultimately going to pick u equal to tangent, because again, the derivative of tangent is secant squared. And so if we look back, we have to go through all the remaining terms in our integral and convert all of them into tangent terms. So this tangent to the 6, that's fine, but we had to do something with that secant squared. And what we did is use that trig identity to convert it into 1 plus tangent squared. And so once we get rid of all the remaining secant terms here, now everything's in terms of tangent, we can go through and actually do our substitution that we wanted to do. So we're going to let u equal tangent. That means du is secant squared x dx. So we plug in all our pieces, and we get the integral of u to the 6 times 1 plus u squared du. Now, this is a product of two u terms, so we have to first multiply this out. So it's a product. So we're going to multiply that to the 1, and then we'll also multiply that to the u squared. So that gives us, the integral of u to the 6 plus u to the 8, if we multiply things out. And the nice thing there is everything is a power function. So now we can actually just use our power rule. So what's the antiderivative of u to the 6? Well, it's 1 over 7 u to the 7. And then what's the antiderivative of u to the 8? Well, it's 1 over 9 u to the 9. And then we put our plus c constant. And then finally we convert back. So this is just regular substitution. We're going to convert this antiderivative back to our original variable, which was x. So we end up with 1 over 7 tangent raised to the power 7 plus 1 over 9 tangent x raised to the power 9, and plus c. So there we go. We have our antiderivative. All right. So let's try that one again. And let's just see what happens if we tried factoring off a secant times tangent. So, going back here, what did we end up doing? We actually factored off a secant squared. So we have two options for how to kind of go through these. We can either factor off a secant squared, or we can try factoring off a secant x tan x. And let's just see what happens if we make the wrong choice, just because that might happen when you're working on some of the problems for yourself. So let's try making the wrong choice. You know what happens. So let's try factoring off and what we're going to see is we're going to run into trouble once we try to convert all of our remaining trig functions into a secant. All right, so let's see what happens when we factor that off. So we're going to have the integral of tangent raised to the power 5. So I'm going to take one of the tangent terms from here. Then I'm going to take one of the secant terms from here, so I'll have secant cubed. And I'm going to kind of group them together, and I'm going to put them next to my differential dx. All right, so if this is what we're hoping ultimately is going to become our du. We're hoping that it's going to become secant times tangent. And if that's what we chose, what is the u term that gives us secant times tangent? Well, it has to be secant x. So the derivative of secant is secant times tangent. So going up to our integral here, what's going to happen? Well, we have to convert everything here into secants. So the secant cubed is fine. That's already a secant term. But that means we have to convert this tangent raised to the power 5. And we have our trig identity that says 1 plus tangent squared is equal to secant squared. But the issue is this only works if we're converting between even powers of tangent and secant. So, we're gonna if we broke this tangent raised to the power 5 up, I mean we could write that as tangent squared x times tangent squared x times tangent x. And what's going to happen is, we'll be able to do something with this tangent squared because we have this trig identity. We'll be able to do something with this tangent squared, again, because of that trig identity. But now we just have a tangent term. And this trig identity doesn't tell us what happens if we just have a tangent. So we're going to run into trouble. So, this is just an example of something you might, if you make the wrong choice for what to factor off, what you might run into is this trig identity only works by really converting even powers of tangent and secant. So if you make the wrong choice, generally what you'll see is you'll get stuck here converting some of those trig functions to the other one. And so in this case, we're going to get stuck. We're not going to really be able to convert this one lone tangent term over to a secant. We'll be able to do some of them, but not all of them. And that kind of gets us stuck when we need to go do the substitution. So if this happens, well, you tried factoring off secant x times tangent x. You got stuck. It didn't work. Try the other one. So go back, scratch all this out, cross it out, and then try factoring off secant squared and see if that helps. So, it's perfectly okay. Sometimes you forget. Sometimes you make the wrong choice. it's okay. You just cross it out and then try the other one, and hopefully that one helps you better. All right. So let's try one more example just to see how these work. All right, so we have, what do we have? We have tangent x raised to the power 5 times secant x raised to the power 7. And we see that we have an odd power of tangent here. So what does that mean? Well, it means we're going to factor off secant x times tangent x. So let's try doing that. So just like before, just like we kind of did in that wrong choice in the last example, we're going to take one of the tangents from here. So that'll give us tangent x to the power 4. We're going to take one of the secants from here. So that'll give us secant x raised to the power 6. And we're going to take one of the tangents, take one of the secants, and we're just going to group them together and put them next to our dx. So when we look at this, that hopefully is, if everything goes according to plan here, hopefully that's going to become our differential. So we're ultimately going to be doing a substitution rule. So hopefully that's going to become our differential du. Well, what does our choice for u then have to be? We're kind of working backwards here. We're starting with our differential. We know for substitution rule, it really, things work out. We know it's going to work out when we get to the differential. So we're kind of starting with the differential, saying, all right, this is what we have to work with. What choice for u can we do in order to make things match nicely? So we're saying, all right, this is going to be our differential, secant times tangent dx. Well, what choice for u is that? Secant. Derivative of secant is secant times tangent. All right, so it helps to write this down first, because then that tells us, back up here, all of these remaining pieces, we have to convert everything that we see in here. Forget about the secant times tangent. We have to convert everything that we see here into secants. All right, so this secant raised to the power 6, that's good. We're done with that. We have to do something with this tangent x raised to the power 4, and we know that secant squared is equal to 1 plus tangent squared x. So we know how to convert even powers of secant and tan. And that's what we're going to do here. We're going to break this tangent x raised to the power 4. We're going to break this up into 2 copies of tangent squared. So we'll write it as tangent squared times tangent squared. And then that secant squared, we're good there, or secant to the power 6, we're good with that. We don't have to do anything there. And then we're also good with the secant x times tangent x next to our differential. And what we want to do is we want to go through and convert each of these tangent squareds here using that trig identity. So let's just rewrite that trig identity where we've solved for tangent squared. So tangent squared, if we solve for it here, we're just going to subtract 1, move the 1 to the other side. So this is going to be secant squared x minus 1. So going down here, let's just fill that in for tangent squared. So we're going to end up with secant squared x minus 1. That's our first tangent squared. Then another one, secant squared minus 1. Then we have our secant to the power 6. And then we have our secant times tan, what's going to become our differential. So, it's looking like a lot here. But we know, kind of by design, this is going to become our differential. And then everything that we have here is all now in terms of secant. So we're ready to actually plug in for our substitution. So wherever we see a secant, let's change it to a u. And the differential here at the end matches up nicely, again, by design. So that's secant times tangent times dx. That's just going to become our new differential du. So let's fill in all the pieces. We're going to end up with u squared minus 1 times u squared minus 1 times u to the power 6 du. And there's going to be a little bit of work here, but this is all going to be power functions. So we'll be able to just do a power rule a whole bunch of times. All right. So let's try that out. Let's keep going with this one. So far, what we've seen is we have the integral of u squared minus 1 times u to the power 6 du. And we're in the process of doing a u substitution, so I'm just kind of doing a little recap here, just so I can refer back to it. And there's a little bit of work that we need to do with this. We need to multiply everything out. So let's actually go through the multiplication. So how are we going to multiply it? Let's start with the u squared minus 1 times u squared minus 1. Let's multiply that out. So you might remember it as FOIL, or however you remember it. The way I think of it is I start with this first u squared, and I just distribute it to both pieces in this second term. So when I do that, I get u to the power 4 minus u squared. Then I take my second term, the negative 1 here, and I just distribute it to both in the second piece. So I get a negative u squared again, and then I get a positive 1. Negative 1 times negative 1 is positive 1. And then I still have my u to the power 6 du. Consolidate as much as you can, so we have two negative u squareds, so we can do a little bit of simplifying there. And then finally, we still have some multiplication, so we can't integrate just yet. We have some multiplication, so we're going to take this u to the 6 and just distribute that. So there's 3 terms inside the parentheses. We're going to distribute it to all 3 terms. So when we do that, we end up with the integral of u raised to the power 10 minus 2u raised to the power 8 plus u raised to the power 6 du. And now this is nice because each of these is just a power function, so we can just use our nice simple power rule. So what's the antiderivative of that first one? Well, it's 1 over 11 u raised to the 11. The second one there is negative 2 over 9 u raised to the power 9. And then the last one is plus 1 over 7 u raised to the power 7. And let's not forget our constant c there at the end, our plus c. And we're in pretty good shape. We're done with the integration at this point. So now all that's left to do is to take our secant, which we know is u, and plug it in so that we can convert back to our original variable. So wherever we see a u, we're going to change it to a secant. So when we do that, we end up with 1 over 11 secant raised to the power 11 minus 2 over 9 secant x raised to the power 9, and then plus 1 over 7 secant x raised to the power 7, and then our constant c at the end. So there we go. We have our antiderivative. So that's really the main technique we're going to see for integrating these powers of tangent and secant is to try and do a substitution. So what we'll see next time is, if we kind of go back to our strategy here, this first strategy generally works if we have an odd power of tangent. This strategy works if we have an even power of secant, but that doesn't cover all cases. You know, what happens? So the question is, what happens if tan x is even and secant x is odd? We're going to answer that next time. So right now, you know, these are our two main strategies. It's to try to do a substitution, and you know, we start by factoring off a secant times tangent or a secant squared, and a lot of times these two methods are good enough. They'll be able to help us finish the integration. But they don't cover all possible scenarios, and as we'll see next time, if tangent is even and secant is odd, it's not going to be such a definitive answer. So we're just going to have to look at sort of a hodgepodge of techniques, but we'll see that next time. All right, so that'll do it for today. Hopefully this is enough to really get us started on integrating these powers of secant and tan. And for the most part, you know, these are the two main things we try first. Try a substitution rule where we start by factoring off either a secant times tangent or a secant squared. But we'll answer this question more tomorrow. All right, we'll see everyone then. Bye-bye.